The third quiz question looks at a cart that's rolling along a flat surface with no friction in the wheels. So if there was nothing being added to it, there'd be no force required to keep it moving. It's moving at 5 meters per second, and there's a jet of water coming straight down into it, vertically down into it, that's got this size and velocity. And the question is, what does this force have to be, given that there's this jet coming into it, in order to keep the cart moving at 5 meters per second? Now, to simplify this problem so that there's no net addition of momentum to the control volume, what we need to do is look at our control volume here in a moving frame of reference. So let's put the whole thing in a frame of reference that's moving with the cart. So the cart is stationary in our new frame of reference. The total momentum of the cart in our new frame of reference is 0. Even as we add more and more water to it, its momentum is still 0. So we're not increasing the momentum of the cart in our moving frame of reference. We can write that the sum of the forces acting on the cart must be equal to the momentum going out of the cart in the x direction minus the momentum coming into the cart in the x direction. Now, once we go to a moving frame of reference of 5 meters per second this way, then the jet's no longer coming down, straight down into our control volume. It now is moving downwards, certainly, but also with a component backwards of 5 meters per second. 5 meters per second in that direction is the rate at which this is approaching the moving frame of reference. So the force F applied in the positive x direction, where this is positive x, there's no momentum going out of the control volume, so that's 0, minus the momentum coming into the control volume. The mass flow rate at our control volume boundary here is the same as the mass flow rate up here. It's all still coming down. It'll be rho density times pi d squared over 4 times area times the velocity at which it comes through, times the u component of velocity that it comes in with, and that's negative 5 meters per second in the x direction. And that gives an answer of 3,142 newtons. The second part of the question asks, what angle would the 20 meter per second jet have to be at 3 meters above the surface, the same location we knew before, for the same mass flow and no force required to push the cart? So, with it coming straight down, we have to push the cart this way in order to accelerate the fluid that had a 0 x velocity as it came in up to having a 5 meter per second x velocity when it eventually settles in the cart. If we wanted it to have no force involved here, then in order for that to happen, we'd have to have the jet come in with the same amount of x momentum as it's eventually going to have when it settles in the cart after it splashes around for a little while. The result is going to be that this needs to have a velocity component of 5 meters per second in the positive x direction, just like the cart does. So for no force, the incoming x component of velocity has to be equal to 0 in the moving frame where we're doing our calculations. That says it's got to be equal to 5 meters per second in the stationary frame. So that has to be 5 meters per second. If that's our v, our 20 meters per second, if we're just taking our jet and turning it like that somehow, then sine theta will be u divided by v. U over v is sine theta if v is still 20 meters per second. Theta then is 14.5 degrees, and that gives us our relationship for what the angle has to be in order for the force on the cart to be equal to 0. It'll still have a u velocity of 5 meters per second on impact, so if it comes in at the top with 5 meters per second x velocity, and we neglect air friction and other stuff like that, then when it gets down to the bottom, going into the cart here, it'll still be moving in the x direction at 5 meters per second. It will, however, be going faster in the y direction than it was up here because it's accelerating as it comes down due to the force of gravity. So gravity will increase the value of the v velocity, the y component, but still no force to push the cart.